Hi everybody, I'm back. Sorry about that. I realized I didn't have any water, so I need to get that. Let me turn this down, and then I'll answer this question about the college reopening. I honestly have no idea at all. So every time we go to a department meeting, I ask them, so when do we get to go back? And the answer is always, well, we're thinking about fall, but nobody knows. And that's been sort of the answer for months now. So I know that summer is still online. And obviously spring would still be online too. They wanted to bring everybody back for fall, but it's really going to depend on vaccine rollout. So like, how quickly can everybody be vaccinated in the community and in the community college? So like I've told them I'm not going to teach in front of students unless I am vaccinated. Like, just no, that is not a thing that I will do. Find someone else. And they respect that decision because obviously I care about my health and the health of my students. So I know that faculty for community colleges aren't really on any of the vaccination plans. So like in some states, like K through 12 instructors are being vaccinated before general public. I don't think that that's true of college instruction here in Washington. So that pushes back the in-person date further, but I don't know what the final verdict is because that's ultimately up to the college president. So I wish I had a better answer for you than fall question mark. Probably, maybe not. I don't know. We already did this question, so I was going to go to this question. So we're going to finish Unit 13 today. Remember, I'm not going to cover combustion analysis because you'll cover it in 162 in more detail. And we have other things that we can do that are more or less the same thing. So on Thursday last week, we talked about how to determine empirical formulas. And just in case you've forgotten the general procedure on how to do that, to find the empirical formula of a compound, you want to first find the masses of the elements that are involved. And you want to convert to moles. And then you want to make the formula, which will involve using the pseudo formula. So that process we did for several problems. We're going to do that again today for one or two problems. And then we're going to jump into balancing equations. All right, so let me clear that off the screen. Now, remember that when you do an empirical formula problem, you get an empirical formula as a result. The empirical formula might not be the actual formula of the compound. What we want is the molecular formula. So the molecular formula is the actual compound. Oops, I highlighted the wrong molecular. There we go. The molecular formula is the actual mass of the compound, or not the actual mass, the actual formula of whatever it is we're looking at. Now, in order to figure out the molecular formula, you need the molecular mass. Now, finding the molecular mass of the compound is actually pretty trivial. We can do that by using a device called a mass spectrometer. And what that spits out is the mass in AMU, or grams per mole, of the thing that we're working with. And then all it takes is we just compare the empirical formula and the molecular formula in the following way. So if I know the mass of the empirical formula and I multiply it by some constant, I should get the molecular formula mass. Or in other words, if I just rearrange this, molecular formula mass divided by empirical formula mass is n, the multiplier. The multiplier is what you multiply the empirical formula by to get the correct molecular formula. And you do that for all the coefficients. So if the multiplier was 4, You'd multiply each element's number by 4. All right, so let's do an example of this. So, sorry, I was chewing my fingernail there. So suppose that you have an empirical formula, CH. And then I weigh the actual compound using mass spec, and I return, hey, what you put in the detector weighed 78.11. Well, let's look at what CH weighs. So we're going to go to Lentech to do that. So let me get Lentech out real fast, because I forgot we were doing that. And when I put in CH in the computer, it says, oh, CH has a molar mass of 13.02 grams per mole. Oh, I'm working in AMU, so let me just do AMU. So if I divide those two things together, I get this. And so what I can say is, okay, if the multiplier is 6, I'm going to multiply each of the substances by 6. So this must be the molecular formula. Now, it is possible for the multiplier to be 1, in which case the empirical formula and the molecular formula are the same. But you should always get an integer when you do this process. You should not get a fraction, because you cannot multiply your number by a fraction and get a whole number as a result. All right, so let's do another example here. Actually, let's have you do an example. Okay. I'm going to give you butane-dione. And so here's the mass of the compounds that I get for butane-dione. First, what I want you to do is tell me the empirical formula. And then I'm going to tell you the actual molar mass. So once I start seeing some answers in the chat for what the empirical formula is, I'll hit the next button, and then you can get the molecular mass of it to find the molecular formula, okay? So first, find the empirical formula like we did last week. And we'll go over the answers to that after I've revealed the next part of the question, okay? See you in a bit. All right, so now that you found the empirical formula, using your empirical formula, tell me the molecular formula if this is what the molecular formula weighs. All right, 1 or 2 more minutes, we'll go over the answers. All right, let's see here. So, oops, hold on. Let's start by, we've already got the masses already figured out. I didn't give you a mass percent, so you could just use these masses as written. I want to zoom this in because it's otherwise going to use too much space. Let's turn all these into moles. All right, so I'm going to turn grams of carbon into moles of carbon. And in 1 mole, there are 12.011. That's too many ones. Grams of carbon. My pen kind of lagged there. That was... Okay. I got to punch that in the calculator. What do we got here? I'm going to turn my calculator on. Oops. I get 2.323, looks like. All right. Then we got hydrogen down here. We'll do the same thing here. So grams of hydrogen, moles of hydrogen. .484 is what I got here. Oh, I'm writing grams. What am I doing? Thank you. I'm not paying attention to what units I have here. I'm having a brain dead day, apparently. I think we're all exhausted with just the state of the pandemic and everything. So we'll do the same thing for oxygen, 18.59. Did I hit the right button? I did. Okay, 15.999. All right, so there's my moles right there. We're going to make a pseudo formula out of that. So C, H, O. That doesn't look like any formula I've ever seen, so we're going to divide by the smallest number. I get 2.000 a bunch. H, this is probably going to be a 3, right? Yep, 3.00008. And then just O. So this formula right here, this is my empirical formula. Oh man, I don't know if I could do in-person class right now. For the reasons that I mentioned before, like... I'm a big proponent of, like, we should just shut everything down and pay everybody to stay home for 2 or 3 weeks. Just supply people with whatever money they need. Yeah, rack up a bit of debt for the government, whatever. Like, put people's safety first, and then we'll be more or less done. But no. Gotta keep the gears of the economy turning. Ugh, grumble, grumble. Anyway, here's our empirical formula. What is the weight of this? We're going to type that into Lentech. So C2H3O. I have C23H3O. That's not what I want. And so the empirical mass of this is 43.04 AMU. And so let's use the rest of the problem. So I know that the empirical mass is what we just calculated, and the molecular mass is reported to be 86.09. So molecular mass divided by empirical mass equals the multiplier. So that would be 86.09 AMU divided by the number we just got up here, 43.04 AMU. AMU cancels out, and the multiplier becomes 2. So I'm going to multiply my formula up here by this multiplier. So C2 becomes 4, H3 becomes 6, and O1 becomes 2. So that is my molecular formula. And there you go. So that's how you do the calculation. So it's just like the empirical formulas that we've been doing all along, except we're going to add in that one step at the end where we compare the mass of what we calculated in AMU to what we actually have determined experimentally. All right. Any questions about that? Let me know. I believe that that's the last slide that we're going to cover, because this should just be, yeah, this is combustion analysis. I'm going to talk about what combustion analysis is, but we're not going to do any problems in here. So, just so that we can get through this. So, what combustion analysis is that whenever you burn something that contains C's and H's and O's, you get these as your product. So, in the next chapter, we're actually going to do something like this. So, let's suppose that I have, like, glucose or sugar or something. If I combust that with oxygen, the results are this. Now, we haven't actually talked about balancing equations or even writing equations yet, which is kind of why I want to skip over this for now, because we don't really have much basis to work with. But what we can do is we can say, okay, well, if my compound has carbon in it, here's that carbon, all of it would end up here. So when you burn carbon with oxygen, all of the carbon ends up as carbon dioxide. Same thing with hydrogen. Let me get a different color for hydrogen. If I react my hydrogen with oxygen to combust the hydrocarbon or carbohydrate that I have right here, all my hydrogen ends up in water. So what that means is that by burning compounds that have C, H, and O in them, and realizing that the products are always going to be H2O and CO2, what I could do is I could weigh these things. I could weigh the water, and I could weigh the CO2. So if I knew what the mass of, say, CO2 was, I could turn that into moles. And I could turn that into moles of carbon, because this would be, for every CO2 I use, I make a mole of C. And then you can get a formula out of it that way. So this is just making the empirical formula process slightly longer by adding extra steps in the front end. Instead of me giving you masses of elements, I'm going to give you mass of CO2. And so this is typically how elemental analysis is done. Is you just burn everything and then you get oxides of everything, and you can weigh those oxides. And so if you look through these problems, you can actually do these for exercises if you'd like to, but we're not going to. And then the oxygen versions are a little bit more difficult, but we have enough stuff that we're going to do. So I'm just going to skip over this and go straight to the end here. There was no sound effect because I didn't have the audio here. So we'll call that a day for Unit 13. And we'll just go on to the next unit, which is much more important, I think. So I need to... There we go. Yeah, I need to discard that. So the screen will be blank for just a second. I got to open the next slides, which I'm in the wrong folder for because I don't know what that is. There we go. So let's balance some equations here. This is much more useful. Boop, there we go. Hey, we might finish this slide too. Or these slides. There's only 20 of them, so... Alright, so what we're going to start doing now is we're going to start looking at reactions and writing them in equations like this. So this is kind of the meat and potatoes of chemistry. You see chemical equations all the time. And what we're going to do is we're going to learn how to interpret them and also write out like what specific terms mean, how to turn words into statements that look like this, and so on and so forth. Now, on the screen, I have two reactants going on. So I have some substance A and some substance B. And when I mix them together, I create the product, and I call the product AB. Okay, that's great and all. Now, let's suppose that I put 10 grams of each of these things in. If I put 10 grams of A in and 10 grams of B in, and everything reacts completely, the result would be I have 20 grams of AB, because all 10 grams of A reacted with all 10 grams of B. Now, this is a universal statement that just always applies to every chemical reaction that we do. Whatever mass of the reactants you put in is the mass of the products that you get out, provided that all of the reactants react. And so this is called the conservation of mass. When you do a chemical reaction, all you're doing is rearranging your matter. You never create matter, nor do you destroy it. You have to use what you have, and you can't trash any of your substance. Okay, so with that in mind, we can make some statements about reactions and do some predictions. If all of my stuff reacts to form products, then whatever substances I put in there must make up the products. That seems like a duh sort of statement, but when I throw sentences at you like this, it gets a little bit confusing to try and parse all that, right? There's a lot going on in that sentence. Sodium metal reacts vigorously with water to produce sodium hydroxide and hydrogen gas. The first thing that you're going to want to be able to do is identify all the chemicals and the compounds. So, for example, what is sodium metal? You know what that is. That's just this. Oops, that's not the pen. There we go. What is water? That's this. What is sodium hydroxide? So that's a little bit more difficult. And then what's hydrogen gas? Well, that's actually a bit trivia. You might want to say, oh, it's H, but it's actually H2. How would you know that? Well, we're going to talk about that on the next few slides. And then I have these indicators that are written after stuff. What the heck does all of this mean? Well, let's go over it one step at a time here. So the first thing that we want to talk about is, where does stuff go on this reaction? Like, what goes on the left and what goes on the right? Well, anything you're going to react is a reactant. These are the things that you're going to mix together and throw in the container that you're going to use as your vessel. Reactants always go on the left of your equation. What you produce is your products. This is what you make after you've combined your reactants together. Products always go on the right. Now, these statements are true as long as the arrow is pointing from left to right. So here you can see that I have a forward arrow written. Now, later on, what we're going to be doing, and when I say later on, I mean 163, you're going to have reactions that look like this, where the forward reaction would be A reacts to form B, and then the reverse reaction would be B reacts to form A. So it's much more appropriate to say that the reactants are at the tail of the arrow, and the products are at the head of the arrow. And that the orientation of the arrow can change. However, it is convention to write for at least introductory chemistry. We always do left to right because that's the direction that we read. We would have the reactants on the left and the products on the right. Now, if you are working in a different language, so for example, Arabic reads from right to left. So I would actually predict that if you were writing a reaction in Arabic, that the reactants might be on the left side, but the arrow would be what tells you what's going on there. So That's something to be mindful, is that I'm not sure if this is universal, but since we read left to right, we're going to write our equations like this, with the reactants on the left and the products on the right. What do these indicators mean down at the bottom here? What these are phase indications, and these are written specifically so that you know what type of matter you're working with. For example, if you had sodium written as a liquid and you try to do a reaction with sodium as a solid, you might not get the expected result. Either the reaction might go too slow or too fast, or something would differ if you used a different phase. For example, if I combine sodium with ice, H2O as a solid, would I get a different reaction? I would get the same products, but how the reaction went would be limited by, the sodium can only react with the ice where they touch, as opposed to I drop the sodium in the water and the water covers the entirety of the sodium, so it reacts much more quickly. So phases can be a useful indication both of like the conditions you should use, or if you're doing this for the first time, for example, of the phases that you would expect. So this right here would tell you, oh, I should expect a gas as a product. So you aren't surprised when you see bubbles coming out or a flame igniting the gas that is released. So what do each of these symbols mean? You're familiar with the three phases. We started chapter 4 with the three phases. Oh, excuse me. Those phases are solid, liquid, and gas. There is AQ, which is a special phase. This is called the aqueous phase. In the aqueous phase, the substance is solvated in water, and if the substance is soluble and ionic, it will dissociate into ions. So in an ionic compound like sodium hydroxide, it's soluble, and we would find these ions present in the aqueous phase. We're going to talk more about that in Unit 15 and 16 when we talk about solutions. Unit 16, actually, for this one. And then finally, we have these numbers on the front. What are the numbers for? Why can't I just, why do I need these numbers? The answer is, I need the numbers in front so that I have the same amount of matter on both sides. So the numbers are to balance the law of conservation of mass. For instance, let's suppose that I didn't have these numbers here. So I'm going to just take the white pen and go like this. We're just going to get rid of these. And then what I'm going to do is I'm going to look to see what happens if this reaction occurred as written. So I should get a different color than black here. I would take this sodium and react it somehow. So where does the sodium end up? Oh, it's right there. So that one's good. All right, where does the oxygen end up? Oh, there it is. That one's good too. All right, where does the hydrogen end up? So here's my hydrogen. And it ends up here and here. But I have an issue. I only started with 2 hydrogen, and this reaction is suggesting that I ended up with 3. Now, you can't turn 2 into 3. That would be creating matter out of nothing. So, the reaction as written is incorrect. I do not react 1 sodium with 1 water to make 1 sodium hydroxide in a hydrogen molecule, because that would be creating matter. So what the numbers in front do, the 2's that are going to reappear here once I hit erase all ink, those 2's represent the number of molecules that I need so that the conservation of matter is satisfied. Now if I check hydrogen here, I have 4 total hydrogen, here's 2 of it, and here's the other 2. So now I have a complete description of what is actually happening here. This process is called balancing an equation, and we're going to show a stepwise way to do it in a second, but you always have to have a balanced equation before you can do anything with a reaction. Since we're going to be using balanced equations to do calculations in the next unit on Thursday, this is going to be super crucial to make sure that our equation is balanced. Now, how do you write an equation from a statement? That equation that I wrote before where sorry, not the equation, but the statement where I said sodium metal reacts with water vigorously to form yada, yada, yada. Writing out the substances can be difficult depending on what phase or what type of substance we're looking at. For instance, if you see a compound, write the formula of the compound. So if I say like phosphoric acid reacts with, you would say, oh, okay, well, I know what phosphoric acid is. I can write that. But if I say it reacts with phosphorus, that's different. If I wanted phosphorus, is it just P? Or maybe it's this, or maybe it's something different. Turns out phosphorus is totally this one. How the hell would you know that, though? And the answer is, well, that's what this slide is for. For elements most of the time are just going to be whatever their symbol is. So if the element is a solid or a liquid, you're just going to write this. For phosphorus in particular, and arsenic also, there are exceptions, and yeah, there they are. I don't recommend memorizing these because they will very, very rarely come up. So if you have phosphorus in a reaction, just writing P is probably okay. And if you ended up having to do something like that, I don't think anybody would criticize you for it. But this totally does exist. In the gas phase, for specific elements, we observe that they are diatomic. And those 7 elements that are diatomic are these 7 right here. These are worth memorizing, and I'm going to show you a little thing on the next slide on how to do that. But for any other element that is not those 7, just write the symbol of the element in the balanced equation. So if I'm reacting with carbon, I would just write this. But if I was reacting with oxygen, I would write that. All right, so let's look at these 7 elements on the periodic table. Where do they show up? Here's where they show up. So I don't actually know if I came up with this because I thought I heard it in high school or what, but I have always called these the silly 7. I know some people call them like Broncliffe or something like that. Or Braun H. Cliff or something like that. But the way that I memorize which 7 are the diatomic ones, which ones you got to put a little 2 after when they're in a formula, is you find these elements that have the shape of a 7 on the periodic table with the stem, the vertical part, in column 7. So there are 7 of these elements. They form a 7, although one of them happens to live over here because he's silly. So that's the silly 7. And those are nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. When you put them into the gas phase, they just happen to pair together. And the reason for that has to do with what we discussed when we were talking about covalent bonding back in Unit 10. Why do these elements want to pair together? Well, this is how they satisfy their octet. So anytime I refer to hydrogen gas with a word, you should write H2. If I refer to oxygen gas, you should write O2. And this will always be true. So in 161 or 162, when a reaction calls for chlorine gas, you need Cl2. If you're reacting with iodine, it would be I2, and so on and so forth. All right, so now what we're going to do, I'm going to have you try these, even though this is supposed to be the demo where I do it. What I want you to do is to turn this statement into a reaction. So take the elements and the compounds as shown, draw an arrow, and then write the result. Don't worry about phases just yet. So just write the compounds and the elements in the proper places, and then don't worry about balancing the equation, because we're going to do that later too. Okay. So write out a statement, and we'll go over the answer together in about a minute or so. All right, one more minute, we'll go over the answer. Try and type it into the chat the best that you can. I realize that it's really, yeah, like that. It's really tedious to try and write it in there. All right, so let's go over the answer. This is going to require us to remember how to make ionic compounds out of words. So this is kind of the reason we have the whole naming section, right? So aluminum metal, so we'll start with that. And we're going to react it with copper 2 chloride. So we'll go plus copper 2 chloride. Well, here are the ions that make up copper. We'll put them down here. So copper 2 would be that, and chloride would be that. I would need a second one of these for the charges to balance out. So that would be our compound. The solution reacts, so we'll draw an arrow, to form copper metal, okay? And then aluminum chloride. So now we gotta do the same thing with aluminum. So here's aluminum. This is the ion that it forms. And then chloride again. I'm gonna need 3 of those. And so that would be my formula. There you go. Now, on the bottom here, I told you not to worry about the phases. But in case you were curious about what the phases were, there they are. We're going to show how you know when to put AQ versus when you put S in the solubility unit in Unit 16. So don't worry about that yet. And also, this reaction is not balanced. So if it looks like, oh, I'm creating chlorine, yeah, you totally are when you are looking at it like this. The actual balanced equation would look something like this. That way we would not be creating chlorine out of nowhere. But we're going to balance equations in the next section. So it says chapter 13 now. That's old. That's the old format. So this is unit 16. All right. So what we're going to do is we're going to take our break right now, I think, because I would much rather have it now than like in 15 minutes after we've done all these problems. So we're going to not do this just yet. We're going to take our break real quick. That's not the break time window. There we go. So I'm going to go back to, let's see here, to here. We'll hit play and we'll have some more Final Fantasy World Map music. We'll see you in 10 minutes. And then we'll start writing some more equations and we'll start balancing them. So see you in a bit for that. Whoops, I'm not paying attention. All right, where were we? We were making chemical reactions here. So I'm going to put a bunch of these statements on the board here. I don't know why that's there. That should not be there. And what I want you to do is, just like before, make a chemical reaction out of these statements to the best of your ability. For any compound, make sure you're putting the compound together correctly using the naming rules that we discussed in Unit 12? 11. Unit 11. All right. We'll go over the answers about 5 minutes or so. So see you in a bit. I went to edit the slide and everything disappeared. So there you go. It's back now. All right, 1 or 2 more minutes. We'll go over the answers here. All right, let's go over the answers here. So I'm going to need to go to this page. Oops, got to clear all that out. Boop, boop. Hold just a second. I hit mute because I thought I was going to sneeze, but I didn't. So I might sneeze in a second here. All right, so calcium metal, so that's this, reacts with water. So I specifically mentioned that it is reacting with water, so we're going to include that in our reaction here. Reacts to form calcium hydroxide. So first off, let's figure out what calcium hydroxide would look like. So here's calcium and here's hydroxide. I need a second one of these to balance out the charges. So that would be calcium OH parentheses 2. And then hydrogen gas. Oh, this is aqueous. Don't worry again too much about the phases just yet. And then hydrogen gas. Hydrogen gas is H2. So there's the first one. I mean, I got to cover it up real quick to do this. So now let's look at the second one. So hydrogen gas and oxygen gas react violently to form water vapor. There you go. And then for the last one, mercury 2 oxide. So let's write down mercury 2. So that's Hg with 2 plus. And then oxide is 2 minus. Those just cancel each other out immediately in terms of charge. So HgO will decompose into mercury and oxygen gas when heated. Now again, phases. How the heck do you know that mercury is a liquid? You can look on the periodic table to see that, but you would not know that just off the top of your head unless you were familiar with mercury. All right, so that's the gist of where we're going here with these types of reactions. And then in the next section, what we're going to do is we're going to start balancing these. So obviously they're not balanced yet because I'm creating and destroying matter at a whim for these reactions. But in this next section, we're going to talk about how to balance them. So let's get started on that. So whenever you balance an equation, you need to have the same number of each thing on both sides. It's really important that you do that because if you are creating or destroying matter in the equation that you've written and then you try and use that to do a calculation, you get the wrong result. So first things first, whenever you are given a reaction, always check to make sure that your equation is balanced. If you are the one doing the balancing, double check to make sure that it is actually balanced. If it's not, again, everything falls apart. So be really mindful. It's super easy to make a mistake. Now, in order for a chemical equation to be balanced, you're going to check each type of atom excuse me, on both sides of the equation. If you have the same number on both sides, you're good. Move on to the next element. Do that for all the elements, and then everything is fine. Now, if you don't have the same number of atoms of each type on both sides, what's going to happen is you're going to need to modify the coefficients in front of each substance, either on the products or the reactant side. It doesn't matter which side you put numbers in overall. Obviously, putting it on one side versus the other will depend on the problem that you're looking at. So let's do an example here. So the way that I like to do these is first thing is first, I draw a big line down the middle. So that line separates the reactants from the products. I will always count things on each side of that line to check them. And so then what we're going to do is we're going to line up the different elements that we have available and just go like this. So I have carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. And so let's count it. Let's start counting these. So there is 1 carbon. There are 4 hydrogens on this side. And there are 2 oxygens on this side. On the other side, I've got 1 carbon. I've got 2 hydrogen. And I've got 2 oxygen plus 1 oxygen is 3 oxygen. All right, so I've counted. Oops, didn't mean to erase that one. I have counted all of my elements. Is the equation balanced? No, because I am losing 2 hydrogens and gaining an oxygen, and that's not allowed. So what we're going to do is I'm going to put these blank spaces in front of each of my substances. And we're going to put a number in those spaces. And we're going to see how that changes things. So, for example, if I were to put this number here, then instead of having just 2 oxygen, I would have 2 times 2, or 4. Does that help me, though? Not really, right? So, would that be a good starting point? No, we're going to try and pick things that assist us. So the first thing that we're going to look at is carbon. Well, carbon's already balanced, so I don't need to put a number in front of anything with the carbon. So I don't got to put something here, and I don't got to put something here at the moment. Next, I'm going to check out hydrogen. Hydrogen is 4 on the left and 2 on the right. There's less on this side, so I'm going to work on this side by putting a number in for something that has hydrogen. Well, that's the only spot I can do that is right here. What number would you recommend I put in the blank that I've indicated? Type that in the chat, and we'll do that and see what happens. All right, 2 sounds good to me, so let's put a 2 in here. Boop, there's our 2. 2 increases the number of hydrogens that I have from 2 to 4. And it increases the number of oxygen I have from 1 to 2, but I also have to add the other 2 that are already there. So I had 3 to start, now I have 4. Okay. So now my hydrogen's balanced. Now I gotta go to oxygen. Oxygen on the left has 2. Oxygen right has 4. There's less on the left, so let's modify something that has oxygen. This is the only one that has oxygen. So what number do you want to put there? Yeah, again, it's 2, right? There we go. So now I just check them all. 1, 4, 4. All my elements balance out, so this reaction is now balanced with 1, 2, 1, 2 as the coefficients. And you can double check that. So I have 1 carbon and 1 carbon. I have 4 oxygen and 4 oxygen. I have, oh, sorry. I have 4 hydrogen and 4 hydrogen. Here's 4 oxygens. Here is 4 oxygens. All right. And so my slides are just going to do that for you. There you go. So here's another example. I want you to try this for a little bit, and then we'll work through it together. So go ahead and balance this equation. You do have to play with this one a little bit. And we'll go over the answers together shortly. All right, how are we doing? Got the answers yet? All right, one more minute. We'll go over the answers together. All right, so same strategy as before. We'll just go like this. Those are the elements that I have on each side. So I got how many nitrogen? I got 1. And I got 3 oxygen over there. And then 1 and 2 here. And then let me put down these. Boop, boop, boop. There you go. Okay, so since I have more oxygen on the left than on the right, this is really the only place that I can start. But no number that I enter here is going to help me, right? So if I put a 1, nothing changes. But if I put a 2, I end up with too many oxygen, right? Well, sometimes you just have to do that. And you just have to increase the amount that you have available so that you can work on the other side. So if you try something in this case, what you'll find is that now you have 1 too many nitrogen and 1 too many oxygen on the right, but you can easily fix that by putting a 2 here, and then you're good. So when you're doing these sorts of reactions to balance them, you do have to do this back and forth thing. What you want to avoid is going back and forth and changing the same 2 numbers over and over and over and over again, or the same 3 numbers in a cycle. If you get into one of those vicious cycles, what has usually happened is that you've done an addition error and you've tallied your inventory wrong. And we'll talk about that on the next slide when we get to, oh, excuse me, problems that arise when doing this. So if you balance your equations incorrectly because you counted wrong, you get this sort of like runaway effect where both sides just skyrocket. And that's your cue to just erase everything and start over. So here are my tips and tricks for you to do balancing equations, because this is not super intuitive. You can definitely predict an approach, but this is also a bit of just like, I don't want to say trial and error, but like start somewhere and then just progress from there. And you could start anywhere on these equations that you want to. It's just that some places make more sense to start from than others. Now, if you ever have a polyatomic ion like this, so this is phosphate. If you have phosphates in your reaction, just write phosphates in the inventory instead of P's and O's. That can help you a lot if you're trying to keep the oxygen and phosphate separate from like an oxygenous hydroxide or something. Because phosphate ions are, oh goodness, Oh, excuse me. Because phosphate ions are polyatomic ions, polyatomic ions tend to stick together. They don't really react under most circumstances. So, don't split them apart into individual elements, and you don't have to worry about them in your inventory. That can save you some time. The next strategy that I would recommend, and we showed this at the beginning when we were talking about combustion analysis, is try and predict the fate of your atoms. If you start with benzene, and you know that you're going to make CO2 out of it, you're probably going to make 6 of them because all the carbon have to go into CO2 from that molecule. How many H2O would you make in this case? Well, if I have 6 of them right here, and each water takes 2, I bet I'm going to put a 3 in front of this in my balanced equation. That would balance out the hydrogens. So, knowing where your elements are going to and from helps you make predictions about what numbers you put where, because you're going to have some common factor between those. And then finally, if you get giant numbers, start over. When I say giant numbers, what I mean is stuff like over 100. You're not going to see a reaction that goes above 25 or 30. And even those are extremely rare. And usually the reactant that's involved in that has a huge number is oxygen. For specific combustion problems, you can get large coefficients, but they will make sense when you see them. All right, so I'm going to give you a bunch of these. Oh, sorry, we have one more. We're going to do octane. This is an example of one that would have a really large coefficient here. So first of all, what we're going to do, since we talked about the combustion analysis chapter, you know that whenever you combust something that contains C and H, the products are CO2 and H2O. And I'm leaving a blank there. Oops, wrong pen. So I can do this. Now I want you to try and balance this equation for a moment. Type in what you get in the chat. And then when we go over the answers, I'll show you how you can get to a situation where it seems like something is wrong here. But in reality, there's a simple fix that requires a trick. Okay? So go ahead and try this. We'll go over the answer in about 3 or 4 minutes. All right, how are we doing? It's a little harder, right? This is why we have this example. So let's try and work with this a little bit and see what we can do. All right, so we'll just draw our line through the middle here. And so what we'll do is we'll inventory like always. And so our first move is going to be, let's look at carbon because we have them written down vertically. If you did hydrogen first, you could do hydrogen first. It doesn't really matter. But I've got 8 carbons here, and each CO2 has 1. So a good starting number to put down would be this. So let's see how that changes. So carbon becomes 8. And oxygen becomes 8 times 2 is 16. But then I have 1 extra one over here, so I have to count that too. So that's a weird number to land on, but whatever. Okay, that balanced out carbon. Let's do hydrogen now. There are 18 hydrogens, and each water uses 2 of them. So 9 times 2 would be 18. That would balance it, right? But that changes oxygen also. So now I have 16 from 8 times 2, and 9 more. So 16 plus 9 is 25. And this is where you get stuck, and you say, well, what number do I put here to make this equal 25? There isn't one, right? Because if I do 12, that's 24, and if I do 13, that's 26. So do I do 13 and then just go back and forth and try and fix it? Well, here's a suggestion. If oxygen comes in pairs, what number times 2 gives you 25? And the answer is 25 divided by 2. That would give you 25, wouldn't it? Now, if you're looking at it and going, that's not okay, oxygen can't come in pairs if you have a fraction. And that's absolutely right. Yeah, you're not going to have a fraction in what actually happens in your reaction vessel, right? But this is a mathematical construct. And if I multiply both sides by a number, it doesn't really matter what number that is, as long as I'm doing the same thing to both sides, right? So what I could do is make the equation just work out numerically, and then do what I had to do with empirical formulas, multiply by the denominator to clear out fractions. So I could multiply everything by 2. Let's get a new color here. To get rid of this 2 right here. And in theory, multiplying the entire left side by 2 and the entire right side by 2 should give me the same number of atoms on both sides. It'd just be times 2, right? So let's do that. So I'm going to times the left by 2. So this becomes 2. And this becomes 25 over 2 times 2 is 25. This would become times 2. And this would become times 2. Now let's check to make sure all of our elements are balanced. Well, 2 times C8 would be 16. 2 times 8H10 would be 36. And 2 times 25 would be 50. Okay, let's check on the right now. 16 times 1 carbon is 16. Let's do hydrogen. 18 times 2, that's 36. Now I got to figure out how many carbon I have. So 16 times 2, this is 32. This is 18. 32 plus 18 is 50. So our equation is balanced with the coefficients 2, 25, 16, and 18. And to get there, I had to employ a fraction. But you can always employ fractions whenever you want to, provided you just clear them away later by multiplying the entire thing by a number. Now you'll notice these coefficients that I got were pretty big. This happens with combustion of hydrocarbons, especially if the hydrocarbons themselves are large. So octane is a very large hydrocarbon. So you're going to need a lot of oxygen to burn it. All right, so let's put up the other reactions here that I have for you. Oops, that's just what we did. Is there another one here? Yeah, there is. Okay. Here are 7 reactions that you can balance. I'm going to let you balance these, and then we'll go over the answers in the last 5 minutes of class. And what I mean by go over the answers, I'm just going to write in all the correct answers. Because I think you get the gist of it by now. And I'd like for you guys to have some more practice. So balance these equations, type them in as you get them in the chat. And I'll print the answers on the screen before we go. All right, I'm going to run out of time if I don't go over the answers now, so I'm going to just put all the numbers on the screen here. Let me get a different color. All right, I'm doing these in my head, so 664. This one is 2, 2. So I'm just going to write out all the answers on the screen here. So 2, 3, 4, 3, 6. Oh, that's when I got to count. Hold on. 2, 3, 5, 6, so 3, 4, 7, 6, 3, and then 8 and 12. Yep, that looks good to me. Okay. I believe all those are correct. So you can try these on your own after the video ends if you'd like to, and then here's the answers so that you have them. That's all the time that we have because class is running up to the end of the period. So we're going to close down the stream. This is the end of the chapter, I believe. So yeah, here we go. So you get 2 of these in one day. Look at that. All right. How did I do it so fast? I've done this for like 15 years, so like I don't have to do inventory anymore. I can do this all in my head. And eventually you'll get to that point too if you just do enough of these. But like right now, I obviously do not expect you to do that. So I will give you one equation and you get like 2 or 3 minutes to do it. So there will be a quiz on this. I believe it's the 13-14 quiz. So the next quiz that will be going up, I know another quiz. Holy crap! But they are kind of backloaded towards the end of the quarter. That quiz will be balancing equations, writing out statements, and doing empirical and molecular formulas. So that quiz will go up shortly after the class is over, and you'll have a week to do that too. Make sure that you are doing these, practicing for these quizzes and then taking them, because I need to unlock everything before exam number 2, which is at the very beginning of finals week. So we're almost done. We are very close to the end. There are only 2 units left. Something to note, so tomorrow it says on there extra lecture if needed, and then chapter 14. We've already done chapter 14, so tomorrow will just be a Q&A. If people have questions, I'll be happy to answer them. Otherwise, there won't be much to do. So we'll see you tomorrow for that. Thanks for watching, and let me know if you have any questions either in Discord or email or Canvas. So I will see you Wednesday and then Thursday for chapter 15. Have a good one.